Hello and welcome to the channel CSAI Think Tinker Learn. Today we are going to do a deep dive architectural teardown of two industry titans, Redis and Memcached. Whether you're designing high-scale systems or prepping for a senior level interview, understanding the why behind the memory management, threading, and persistence models is non-negotiable. Before we tear down the engine, please take a moment to like, share, and subscribe. It helps the channel to grow. And also head over to www.bitbytoken.com. I built this as the ultimate companion site for our software, data, AI, and ML engineering. It's packed with foundational concepts and detailed system design guides. Um, we are to provide a bit of a navigation here. So this is the site bitbytoken.com. The link will also be in the description below. Again, I have distributed it across different disciplines, software, data, machine learning, and AI engineering. Each of these disciplines have further articles based on the fundamentals, which are very much searchable. So if you want to look for WebSockets, those details are available under basics, advanced, and experts. In addition to this, we have a sample solutions. We have tried to provide solution as detailed as possible. We work with the functional requirement, NFR, scales, high-level design, data models. We further down have sequence diagrams. We try to break down various concepts around load balancing, caching strategies applicable to a specific design in question. Then we are talking about trade-offs and considerations as well. So have a look at it, provide your feedback, and we'll be waiting on your comments on this so that we can make this site even better. Okay, let's get under the hood of Redis and Memcached now. My next slide. Okay, how do we cache? It's not just to be fast, it's to bridge a physical reality. Look at the latency gap here. CPU cache operates in sub-nanoseconds, RAM in nanoseconds, and NVMe SSD in microseconds. But your disk-based database, it lives in a 10 millisecond range. That's a 1 million x latency gap. Comparing a database read to a RAM read is like comparing walking across the country to simply reaching into your pocket. If you don't respect the physics, your algorithm won't save you. We cache to bring the data into the pocket of our application. The biggest difference between these two is the threading model. Memcached is multi-threaded, designed to utilize all your CPU cores for simple, high-throughput key-value operations. Redis pre 6.0 is famously single-threaded for command execution. This means your commands are serialized. You have zero lock contention. This is beautiful for consistency. However, it also means that one landmine ON command, like fetching a million item list, can block the entire server. Know your threading model before you push to production. How do we handle persistence in Redis then? We have two main weapons, RDB, which is the point in time snapshot for fast recovery, and AOF, a write ahead log that records every operation for near zero data loss. If you rely only on RDB and the server crashes between snapshots, you lose that interim data. In production, we usually run both AOF for durability and RDB to speed up disaster recovery. It's a trade-off between strict durability and restore performance. How do you choose between Redis and Memcached? Use this decision matrix. If you need persistence, you need Redis. If you need complex data structure like sets or hashes, you need Redis. Memcached is for when you are at a massive internet scale and you only need high performance, simple key value lookups while squeezing every last CPU cycle out of the multi-core hardware. But for 95% of the Greenfield project, Redis is the safe default choice. Let's look at the string type. It's not just a string, it's an SDS, a simple dynamic string that tracks length in O1. The classic failure point here is the counter problem. If two app servers read a counter at 10, increment it, and write 11 back, you have a race condition. The fix is atomic server-side operations. Command like INCR, increment, or SETNX move the logic from the app layer into the Redis engine. ensuring data integrity at the memory level. Now the list. Under the hood, it's the quick list, a hybrid of doubly linked lists and compressed arrays called list packs. It's brilliant for producer-consumer queries like Celery or Sidekick. But here is a warning. Random access by index is ON. If you find yourself searching or accessing the middle of a list, you're using a wrong tool. It's designed for push and pop operations at the edges, not for searching. Now the hash. Please stop storing massive JSON blobs in a single key. Every time you want to update one field, you have to fetch the whole blob, parse it, update it, and send it back. That's a massive network waste and a recipe for race condition. Instead, use a hash, which as set, you can perform atomic per field updates. It's faster, cleaner, and list pack to hash table upgrade path makes it incredibly memory efficient. The set is an unordered bag of unique items. Its superpower is server-side set theory. Instead of pulling two massive arrays with Redis to your Python app to find the intersection, just use center. Let Redis do the heavy lifting. It saves you from shipping megabytes across the network, turning an O(n+n) application side nightmare into a streamlined server-side operation. The crown jewel, the sorted set. This uses a dual structure, a hash table for O1 score lookups and a skip list for O log(n) range queries. Why does this matter? Because naive arrays would require resorting on every single insert. An O(n log n) disaster. Redis uses probabilistic skipping to keep operations lightning fast. This is the perfect tool for real-time leaderboards and sliding window rate limiters where the score is a timestamp. Your daily toolkit: set, get, expire, and del. The holy grail command is SETNX EX. Use this for distributed logs to ensure only one worker owns a resource at a time. And don't forget the TTL introspection. Use TTL to check if a key even has an expiry. This is your bread and butter for session management and keeping your cache fresh. A major trap for the unwary is the del versus unlick command. Because Redis is single-threaded, if you try to delete a massive key with a millions of elements, you will freeze the entire server while it reclaims that memory. The fix is unlink. It deletes the key reference immediately in O1 and then frees the actual memory in the background thread. Always use unlink in production unless you have a very specific need for synchronous memory reclamation. Here is your architecture mapping matrix. When you're designing, map your problems to the data type. Need a log? String plus set nxex. Need a task queue? List. User profiles? Hash. Mutual friends? Set. Real-time ranking? Sorted set. This matrix is your cheat sheet for selecting the right structure before you even write a line of code. To wrap up, here is your interview cheat sheet. It asked about the difference between Redis and Memcached, pointing to the threading and the data structure. If asked about persistence, mention the trade-offs between RDB and AOF. And remember, fluency in Redis isn't about memorizing commands. It's about matching the business constraint to the underlying data structure. Now, I have a question for you. Have you ever had a production issue caused by an ON command blocking a single thread Redis instance? And how did you debug it? Let me know in the comments below. Also, do check out my site, bitbytoken.com. Again, the link is in the description below. And don't forget to like, share, and subscribe. And I'll catch you in the next one.